Hi, and welcome to a lesson on the RF noise environment. In previous lessons, we've discussed properties of signals that exist in the RF spectrum. But, modulated signals account only for a tiny fraction of the power that we find in the RF spectrum. The rest is noise. And that noise is the topic of this talk. To get started, we're going to need to start with some kind of definition of what we mean by noise. We're going to do that in terms of a taxonomy of the various things that we find in the RF spectrum, which includes not only proper signals and noise, but also interference. From there, we'll move on to the topic of antenna temperature, which is a common and useful way to describe noise power. And then, of course, we'll want to say something about the antenna temperatures that we expect to see. So before getting started, a preface comment is in order. This lesson is about noise external to receiving systems. Receiving systems themselves generate noise, which we might refer to as internal noise. Now, that's a big deal unto itself, but it's not what we're interested in here. Here we want to talk about the noise that originates out in the environment. Okay, let's sort this out. The initial sorting of power in the radio spectrum might be to categorize signals of interest and then signals which are not of interest. So, let's make that distinction first. Of the signals we're typically not interested in, it's convenient to discriminate between interference and noise. Now, these are not necessarily the same thing, and it's easy to conflate these two concepts. As a way to discriminate, I'm going to define interference as signals which are not of interest and which are concentrated in frequency, and noise as the rest, which then, by definition, is distributed in frequency. In fact, we expect to see noise all over, that is, at all frequencies. Because noise is distributed in frequency, it's usually awkward to talk about the power of noise. What's really more convenient is to describe noise in terms of power spectral density, that is, how much power per unit of bandwidth, as in watts per hertz. Now, I want to make another point about the difference between what we're calling interference and what we're calling noise. Interference can be interpreted as being in one of two categories. The first category is that signals that are not of interest to me, but are of interest to someone else. That usually means radio systems that somehow overlap in frequency, so that each presents some interference to the other. This is sometimes called co-channel interference. For sure, that does not fit our definition of noise. The second category is signals that are not of interest to anyone, and there's an enormous amount of that in the radio spectrum. All of this is unintended transmission. Now, a certain amount of this is from things that have nothing to do with radio. For example, computers, computer displays, computer networking equipment. These are all notorious for producing interference which is concentrated in frequency and is certainly not intended to be received by anyone. Another source of these signals is the same transmitters that are generating the signals of interest. Every transmitter generates a certain amount of unintended power as a byproduct of generating the signals that they intend to transmit. These byproducts include harmonics, intermodulation, and local oscillator radiation. These unintended signals will be discussed in other lessons which concentrate on engineering issues. All that's necessary to know here is that all transmitters generate interference in some form, and you can bet that low quality or improperly designed transmitters, or transmitters which are malfunctioning, these are certainly going to generate a lot of this kind of stuff. Now, the reason I point this out is because, by our definition, this is all interference, and none of this is noise. It's not noise because it is concentrated in frequency, rather than being spread out in frequency. What we're calling noise falls in two broad categories, indicated here as anthropogenic and natural. Anthropogenic noise is noise that originates from human activity. For example, gasoline engines work by detonating gasoline using an electrical spark from a spark plug. That spark consists of highly accelerated charged particles, so there's radio emission. And the spectrum of a very short pulse of radio emission is very broad in bandwidth. And in an engine, that spark is happening over and over, so it's always there, sparking away many times per second. So gasoline engines produce a steady roar of radio emission that's distributed over a broad range of frequencies. In other words, noise. Any form of digital technology will also generate noise, and for a similar reason. Those sharp transitions between bit values generate a very broad spectrum radio signal. And since those transitions are happening at a very high rate, and in fact at many different rates, the result is a nearly continuous broad spectrum radio emission. Yet another notorious source of anthropogenic noise is arcing on power lines. What happens is that power lines are separated using isolators, and over time those isolators deteriorate and begin to fail. And when they begin to fail, they allow current to intermittently arc over from one conductor to another. This becomes just like the spark plug in a gas engine, so once again we have noise-like radio emission. Now, to be honest, any one source of these things alone might not appear to be very noise-like. But when you have many of these things all happening all at once, the combined effect is very noise-like. And we'll see that in a plot that I'll show at the end of this lesson. An analogy that might help understand what's going on here is to consider the sound of a waterfall. You know, any one drop of water going over the waterfall, that only makes a single drip sound, which is limited in time and doesn't amount to much. But when you have many, many, many drops of water going over the waterfall, these all add up, and the sum is heard as the roar of the waterfall. This is more or less what the anthropogenic noise background is like. That brings us to natural sources of noise. So, what things in nature produce radio signals that are distributed in frequency and therefore can be considered noise? Well, a primary culprit is lightning. Just like gas engines and power line arcing, lightning is essentially electrical spark. So, you get a broadband emission for the same reason. And even though there may be no lightning where you are, there is always lightning happening somewhere, and much more than most people imagine. The emissions from all that lightning happening all over the world are able to travel great distances, and so this creates a significant amount of noise no matter where you are on the surface of the Earth. Other sources of naturally occurring noise are due to somewhat different mechanisms. A big one is thermal noise, especially at higher frequencies in the radio spectrum. The idea here is that anything that has heat generates radio noise. And this shouldn't be too surprising because heat is literally particles moving around, and those particles are typically charged. So, for example, the surface of the Earth is a source of radio noise, and the power spectral density of that noise is proportional to the temperature of the ground. Another source of noise that you might not think of is the Sun, and also Jupiter. The Sun produces very different kinds of radio emission, and talking about all that is well outside the scope of this talk. Nevertheless, rest assured that the Sun is more than capable of contributing significant noise power to any receiver that you might care to consider. The planet Jupiter, too, can create surprisingly strong radio noise on Earth. However, this emission is relatively intermittent, and is typically limited to frequencies in the HF and lower VHF bands. People are often surprised to learn that our entire galaxy, indeed, the entire universe, can contribute significant and measurable amounts of noise that's measurable by receivers on the surface of the Earth. Galactic noise in particular can be very strong, and I'll talk some more about that at the end of this lesson. CMB stands for Cosmic Microwave Background, and that's usually not noticeable by systems unless they're designed to receive it, so I won't say any more about that. The bottom line on natural sources of noise is that they exist, and they are often significant. In summary, natural sources of noise certainly exist, and they are often significant. All right, let's take a step back and look at the entire situation. What I'm calling noise is the stuff I've circled in red. Noise, in this context, is unavoidable radio frequency power that arrives from somewhere outside the receiving system, is smoothly distributed in frequency, and is due to some combination of anthropogenic and natural phenomena. So, the question becomes, how much noise are we really talking about here? For that matter, how do we even know how much noise is arriving from outside the receiving system? Well, consider this diagram. This is a receiving system which consists of an antenna and a receiver. This antenna we'll consider to be lossless in the sense that there's no dissipation of power within the antenna. That is, all the power that the antenna captures is available to the receiver. Also, let's be clear that the pattern of this antenna will matter. What we mean by that is that any given antenna will be better at receiving signals from some directions as opposed to others. For example, if we have a simple dipole, then that dipole will pick up signals from most directions reasonably well. If, on the other hand, we have a gigantic paraboloidal reflector antenna with a beam that's only a few arc minutes wide, well, that's going to only be sensitive to noise coming from within that main beam and relatively insensitive from noise in other directions. For the purposes of the current talk, we're interested in the terrestrial radio noise environment, so we should assume an antenna with a very broad pattern. A dipole antenna would do, so that we're sensitive to all of the noise that's out there. So, to be clear, we're assuming the antenna is dipole-like, or at least has a very broad pattern. Now the receiver. We'll assume the receiver is ideal in the following sense. First, it contributes no additional noise to the measurement, so we can be sure we're measuring external noise. But also, it's conjugate matched to the antenna impedance. Now, if you're an electrical engineer, you probably know right away what that means and why it's important. If you're not an electrical engineer, then no worries. All this means is that the receiver is designed to receive the theoretical maximum amount of power that the antenna is able to provide. And that's all you need to know. Now, this receiver makes a measurement, and that measurement is the power spectral density, which I've given the symbol capital S. As I've said before, this has units of watts per hertz. But if we're really measuring noise, then S shouldn't change very much as a function of frequency. Of course, there is some change with frequency, but it should be very gradual. So, in principle, it's good enough to simply measure the power in some small bandwidth and then divide that by the bandwidth to get S, the power spectral density. Now, there's no problem in measuring and reporting noise power spectral density, but that turns out to be a bit awkward for practical work in both engineering and astrophysics. A somewhat more common and convenient way to characterize the same quantity is in terms of antenna temperature. Antenna temperature is usually not a physical temperature. That is, it is usually not actually a temperature. It's simply a way to express power spectral density in terms of temperature or in temperature units. Here's the formula. The antenna temperature T sub A is simply the power spectral density, S, divided by little k, which is Boltzmann's constant. Boltzmann's constant is simply a physical constant that tells you how much energy is available per unit of heat. And that number is 1.38 times 10 to the minus 23 joules per degree Kelvin. Now, this can be a little bit disorienting the first time you see it. One way to see that this makes sense is to consider the units. S, power spectral density, has units of watts per hertz, and Boltzmann's constant has units of joules per Kelvin. Now, 1 watt is 1 joule per second, and 1 hertz is 1 reciprocal second. So, if we consider all that, then we see that the units of antenna temperature are indeed simply kelvins. So true enough, power spectral density and antenna temperature are different only by a physical constant, and these two quantities are expressions of essentially the same thing, that is, the amount of noise. Now, if we have an antenna temperature, and we want to get back to power spectral density, then there's no problem. All we need to do is multiply antenna temperature by Boltzmann's constant, and that's all there is to it. With that in mind, let's look at some examples. Here's a plot of antenna temperature in Kelvin as a function of frequency in megahertz. Here we're considering frequencies in the MF, the HF, and the VHF bands up to about 200 megahertz or so. These curves are what we expect to see in various situations where the antenna is a low-gain antenna, that is, an antenna with a very broad pattern like a dipole antenna. These results come from many measurements which have been distilled down to empirical formulas that best fit the measurements. Let's start with the curve labeled quiet rural. In this case, the measurements are taken at various locations on the surface of the Earth that are far from anthropogenic sources of noise. So, this result is dominated by natural sources of noise originating from the Earth. Now, note that I said originating from the Earth. That's going to become important in a moment. Note that the antenna temperature here is pretty big. It's on the order of 10,000 Kelvin, going up orders of magnitude as we go down in frequency. Now, if you wanted power spectral density in watts per hertz, you just multiply that by Boltzmann's constant, and you would get numbers that are pretty small relative to 1 watt per hertz. For example, an antenna temperature of 10,000 Kelvin is 1.38 times 10 to the minus 19 watts per hertz. Now, that sounds small, but it turns out to be equal to 1.38 times 10 to the minus 13 watts per megahertz, which is about minus 129 dB watts per megahertz. And that an electrical engineer would probably express as minus 99 dBm per megahertz. Friends, minus 99 dBm per megahertz is something that can easily be noticed by a modern receiver. Next, consider the curve labeled rural. In this case, we're considering locations which are considered rural, but not necessarily free from anthropogenic noise. For example, farmland, where the anthropogenic noise is coming from farm equipment and whatever technology people use around the farmhouse. In this case, we see antenna temperature jump up by an order of magnitude. So we see it's quite easy for noise from human activity to dominate over naturally occurring noise. It follows that you would expect to see antenna temperature continue to increase as population density increases, and in fact this is the case. As you can tell from the curves here labeled residential, which is a little bit higher, and city, which is a little bit higher yet. Now, an interesting thing to note here is that we find that antenna temperature in all these cases is given in this frequency range by a simple log linear relationship with frequency. And that formula is in the upper right-hand portion of the slide. To a good approximation, we see that the antenna temperature is proportional to frequency raised to the power minus 2.7, at least in the frequency range shown in this plot. One final feature I want to point out in this slide is the curve labeled galactic. This is the contribution to antenna temperature from radio frequency emission originating from beyond the Earth. Now, that radio emission is dominated by the combined roar of accelerated charged particles located throughout the galaxy. And you might be surprised by how strong this is. Note that it's stronger than natural radio emission originating from our own planet over a broad range of frequencies. Okay, one final comment. This plot only goes up to about 200 megahertz. So what happens above 200 megahertz? Well, that gets complicated. All of these noise mechanisms, and a few more, exist throughout the radio spectrum. In bands above VHF, most of these turn out to be weak compared to thermal noise from the ground, and also weak compared to the noise that's generated internally to a receiver, but not always. And it depends on how sensitive the receiver is, the antenna pattern, where the antenna is pointed, and where relative to sources of noise that antenna is located. My advice to you when it comes time to face this issue in practice is to take an inventory of these factors, do a little research to identify cases that apply to your scenario, and then perhaps follow that up with measurements if you can. For more information about this, and especially frequencies above 200 megahertz, reports by the International Telecommunications Union, the ITU, those can be useful. Okay, let's review the main points. First, we define noise to be distinct from other radio emission in that it is smoothly distributed in frequency and slowly varying in frequency, so that it's best described in terms of power per unit bandwidth. Noise originates from a combination of anthropogenic and natural sources, and I provided a high level and certainly incomplete list of what those sources might be. We introduced the concept of antenna temperature, which is defined with respect to a lossless antenna connected to an ideal receiver. And it's important to remember that antenna temperature is going to depend on the pattern of the antenna. Finally, I showed some typical values of antenna temperature at frequencies below 200 megahertz. I also explained that above 200 megahertz or so, things get complicated, and you really need to consider what's going on a case-by-case basis, considering the antenna pattern, where the antenna is pointed, and where the antenna is located relative to sources of noise. That concludes this lesson on the radio environment. Thanks for listening.